Hi everyone! In this video, we're going to learn how to interpret the results of a millimole reaction table. One of our learning goals is to be able to calculate the pH of the solution at any point along a titration, as the strong base titrant is added to the acid solution. There are 4 general steps we need to follow in order to ultimately calculate the pH. Calculate the millimoles of acid and base, and use that information to set up the millimole table. Interpret the E row of the millimole table to figure out where the reaction is on the titration curve, then calculate pH based on the results of step 3. The calculations and setup of the millimole table are covered elsewhere, so in order to focus on the interpretation, we'll take a look at 3 completed millimole reaction tables, determine what the E row is telling us, and identify where this specific situation lies on the titration curve. Before we get to the millimole tables, though, let's take a quick look at a strong acid titration curve to remind ourselves of what it looks like. A titration curve is a plot of pH versus volume of titrant. This curve begins at a low pH at 0 mils of titrant and increases slowly for a while. When the titration nears the equivalence point, there's a steep, almost vertical increase by several pH units. Then the curve continues at a slow increase until the experiment is stopped. There are 2 points and 2 regions of interest on this titration curve. However, we will not consider initial pH here in this video because there isn't a millimole table involved with calculating its pH. So this leaves us with 3 possibilities. Before the equivalence point, which is the region between the initial pH and the equivalence point, the equivalence point itself, which corresponds to the specific volume of titrant giving reaction completion, and after the equivalence point, which is the region beyond the equivalence point, also known as the situation of excess titrant. What you'll see shortly is that we can align the results of the millimole table to these 3 parts of the titration curve, before, at, and after the equivalence point. I'm presenting the millimole tables here as handwritten, so you can see them in a similar format as you'll be constructing them on paper. Here's a quick overview of the layout. The reaction at the top shows the net ionic equation for our strong acid titration reaction. Our acid, H+, reacts with the titrant, OH-, or hydroxide, to form water. The water is not part of the calculation, so we draw a line through it to remind us just to ignore. The rows correspond to the amounts of H+ or OH- involved in the reaction. I is initial, which is what we're starting with in this particular situation. C is change, where we subtract the lower initial amount from each reactant, and E is end, which is what is left in solution after the acid and base have reacted. In this first example, we see that all of the H+ in solution reacted stoichiometrically with the hydroxide that was added. There's no excess of either reactant, which is the definition of the equivalence point. When both H+ and OH are at 0, the reaction is complete and we are at the equivalence point. In our next example, we see that the hydroxide goes to 0, which means that all that was added was used up. When the titrant is at 0 and the acid is greater than 0, we are before the equivalence point. There's still some H+ remaining even after this reaction. This tells us that the reaction is not complete because some of the H+ didn't react. So this titration is somewhere in region 2. And our last example shows that the original acid is fully reacted because it goes to 0. However, there is excess hydroxide remaining. So here, we are after the equivalence point. There is no H+ left to react with the hydroxide, so the hydroxide begins to accumulate. This situation puts us in region 4. To recap what we learned here, we can interpret the E row of the millimole table to align with different parts of the titration curve. If the H+ is greater than 0 and the OH- is at 0, we're before the equivalence point. If both H+ and OH- are at 0, we're at the equivalence point. And if H plus is at 0, but hydroxide is greater than 0, we're after the equivalence point.